Okay, we're back for more on modeling. Correlation varies between -1 to +1, with 0 being the, oh darn, I have no relationship between my variables. Now I'm happy to report that you are all capable of calculating the Pearson correlation coefficient. Fantastic. But what's the hypothesis test for correlation? So the parameter representing correlation is rho, and rho is estimated by the sample statistic R. So your null hypothesis is that rho equals 0, and rejecting the null hypothesis indicates only great confidence that rho is not exactly 0. And a p-value does not measure the magnitude of the association, but is affected by sample size. And remember, correlation is not equal to causation. You get your results back from a study, and you're really super excited to find out whether or not your hypothesized positive correlation is in the results. So you calculate your Pearson correlation coefficient, and it's positive, and it's significant. Oh, excitement. But then you realize, oh, wait a minute. I remember Pascal and Paul suggesting that I plot my data. All right, I'll do it. And you plot your data, and it looks like this on the slide. And you realize, whoa, that doesn't look linear. And you're right, it's actually quadratic. So is that a problem? Yeah, it's a problem, because basically what it's saying is you are using the wrong equation to model your data. You should be using a quadratic regression, not a simple regression or correlation in order to model your data. So you would need to change up your approach in order to better fit the data. So be careful that a simple regression or correlation analysis is not always applicable to your data. Another example of when you need to be careful using correlation or simple regression is when you have an outlier. So you'll see here in the first data set that your R is 0.02, which is basically 0. Not exciting. But in data set 2 here, you have one single crazy outlier, which is probably a typo, and you have an R value of 0.82. Oh, excitement. Yeah, but be careful. Correlation, or simple regression, is very susceptible to outliers. Here, of course, is what we use in order to calculate correlation in SAS, the CORR procedure, which we've seen before. So let's talk a little bit about simple linear regression analysis. As we've covered in previous lectures, this correlation is equivalent to simple linear regression analysis, and the objectives are to assess the significance of the predictor variable in explaining the variability or behavior of the response variable. Nothing new here. And to predict the values of the response variable given the values of the predictor variable. Here's an example, of course. Let's say you have fitness and you have your predictor as runtime and your response is oxygen consumption. So if you were to graph your data, you're going to have your predictor on the x-axis, your outcome or response on the y-axis. You're going to put your or obtain your line of best fit or your regression line on your graph. In this case, it is a positive relationship. The distance from your origin to the intersect with your y-axis is going to be your intercept, so beta naught in your equation. The equation for your line is going to be your beta naught plus beta 1x, which is your predictor. And your the slope is going to be for every unit increase in your predictor will yield a beta 1 increase in the units of your response. So taking this a little further, you're going to have your hypothesized unknown relationship here in the dashed line. You don't know this. And then you're going to estimate based on your sample your regression line here. That's why you have the little hats. Remember, these are estimates, and this is your predicted value. And the residual, as I said, is going to be your actual value minus your predicted value, meaning that here's your actual value and there's your line of best fit. This distance here represents the residual, or the error, so to speak. Now your baseline model is simply going to be the mean of your outcome or response variable. Let's look at explained versus unexplained variability. Well, if you take the distance of any given point all the way to the mean of your response variable, which is your base model, then that represents the total variability. But within that variability, you'll remember that the distance between your mean and your line of best fit is going to represent the explained variability from the model. Whereas the distance from your data point to the line of best fit is going to represent the unexplained variability, or the error. So once again, you'll recognize this figure, but in this case, we're looking at partitioning the variability in regression. So the total variability, as I've just shown you on the graph in the previous slide, is the sums of squares total. And it's going to be partitioned into the signal and the error, which the signal is going to be your sums of squares regression, which represents your model, and the sums of squares residuals, which represents your error. Once again, the coefficient of determination, R square, in this case is going to be the sums of squares regression over your total sums of squares. And once again, it represents the proportion of variance accounted for by the model. But this time, your regression model, not your ANOVA model. The correlation coefficient, now here's a little tricky one. In the special case of simple regression, then R, your coefficient of correlation, is going to be equal to the square root of your coefficient of determination, R square. But remember, this is only valid when you have simple regression, which means one single predictor to a single outcome. And that's because it's equivalent to correlation, to Pearson's correlation coefficient. Now you'll remember from previous lectures that the Pearson correlation coefficient, R, is equal to the covariance of x and y over the square root of the product of variance of x and y. Now no surprise, the assumptions of the simple linear regression, for every level of your predictor x, you're going to have a normal distribution of the residuals, and the variance between these levels of your predictor will be the same, will be equal. So equal variance and normal distribution of your residuals. This is also called homoscedasticity. That brings us to the end of lecture 1 of part 5. Next up in lecture 2, we're going to start talking about reliability.